Modern computers are extraordinarily fast, and they can do upwards of 5 billion calculations every single second. However, there are some very important problems that could take even our fastest supercomputers more than 1,000 times the age of the universe in order to solve. There's a new type of computer, called a quantum computer, which uses fundamental laws of physics in order to speed up computation exponentially. Quantum mechanics is the area of physics that describes how really small particles, like atoms and molecules, behave. But unlike most other physics, it uses probability and chance. This isn't just a matter of mathematics or semantics. According to quantum experiments we've done, nature is in some way fundamentally probabilistic. But quantum mechanics doesn't just use any old probability. It actually allows for probabilities to be negative. This means that, for example, if you had a particle that was probably over here and another particle that was probably over there, then you'd expect there to be a pretty decent chance that you could find a particle right here. However, if that second particle has a negative probability, the chances might actually cancel out, and it might be impossible to find another particle in between them. This means that certain events in quantum mechanics can actually cancel each other out, and this is the key to understanding how quantum computing works. But for now, let's go to a simple example about just flipping coins. If you flip a coin, you get a value that's either heads or tails. But while the coin is still in the air, you can think of it as being both heads and tails at the same time. If you flip 3 coins, there are 8 possible configurations. Tails, 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 heads, tails, heads, tails, tails, heads, heads, etc. If you imagine flipping 3 coins all at once, while they're still in the air, you can think of them as being in every one of these 8 possible configurations at the same time. And every time you add a new coin, you double the number of possible configurations. If you flip 10 coins, you can get 1,000 different configurations. If you flip 20, you can get over 1 million. And with just 2,000 coins, you can get more possible combinations than there are atoms in the observable universe. If we could use the configurations of coins to do computation, then we could exponentially scale up how quickly we can compute things. The first step of doing that is to convert combinations of coins into numbers. And we can do that very simply by just saying, let tails, tails, tails represent the number 0, and tails, tails, heads represent the number 1, and tails, heads, tails represent the number 2, and so on and so on and so on. Now let's see how we can use that to solve an actual problem. For example, factorization. Factorization is trying to find 2 numbers that multiply to make an original number. For example, if we wanted to factor 35, we could do that by writing 5 times 7, because 5 times 7 equals 35. If we pick a specific number, like 5, we can ask, is 5 a factor? And get out a specific answer of yes or no. However, we can generalize this and ask, is x a factor? We don't get a specific answer out. Instead, we get, if x is 0, then no. But if x is 1, then yes. But if x is 2, then no. If x is 3, no. If x is 4, no. But if x is 5, yes. And so on and so on. If we could implement this algorithm on flipping coins, then because we can get all of the input values at once, we can also get all the answers to our questions all at once. In this sense, we can use probability to get multiple computations at the same time. The only problem is that when all the coins land, you just get a random output of yes or no. You don't get the whole computations output, you only get a specific answer. And this is where quantum probability comes into play. If instead of coins, we use the direction that subatomic particles were spinning, then we could implement this algorithm. And more importantly, we could cancel out all of the wrong answers using negative probability. That would leave us with only the correct answers left. And so whenever we measured the system, we would get a factor. Just like every time we added a coin, the number of possible configurations doubled, every time we add one of these tiny subatomic quantum particles, called a qubit, to our system, the number of possible inputs double. Currently, the biggest quantum computers in the world only have a few hundred qubits, but that still means that the number of possible inputs they can have is over 10 duotrigon trillion. That's this number. This means that the amount of computations that a quantum computer can go through at once is exponentially more than the same number of computations that a classical computer can do. This makes quantum computers extremely good for problems which require a huge number of inputs, like factoring numbers. Because quantum computers are expensive, hard to build, and really prone to error, we haven't really used them to do much computation yet. But as the technology continues to advance, this may be the biggest revolution in computing ever.